Calorimetry Part 2, Enthalpy. Enthalpy is related to internal energy. If internal energy is heat plus work, we are often only concerned with the heat aspect. For example, if I'm cooking something with, say, natural gas, I'm not really concerned about the work energy that is being done by the natural gas, by the expansion. I'm really only concerned with the heat that's produced. Usually, chemical and physical changes occur with static pressure. That means that the pressure is constant. At constant pressure, the amount of heat that is produced by a process is referred to as its enthalpy. Enthalpy, which is abbreviated with a capital italicized H, is the sum of the internal energy and the product of the pressure and volume in the process. So enthalpy is internal energy plus pressure times volume. Both internal energy, pressure, and volume are all three state functions, which means that enthalpy is also a state function. Change in this state function, then, change in enthalpy, is equal to the change in internal energy plus pressure times the change in volume. Heat transfer that occurs at constant pressure is referred to as Q sub P, and this is expressed as our change in enthalpy. So our change in enthalpy is equal to change in energy, internal energy, plus P delta V. If the delta E, the change in internal energy, is Q plus W, and we know that W is negative P delta V, we can rearrange the negative sign such that negative W is P delta V. If I substitute delta E into our enthalpy equation, then the enthalpy is equal to the QP plus W, and then plus the P delta V that was there initially. So delta E has now become QP plus W. Substituting now in the negative W being equal to P delta V, our change in enthalpy is equal to QP plus W minus W. So change in enthalpy is directly change in heat, or just the heat. Now, enthalpy as a state function can be expressed as the change in enthalpy being equal to the enthalpy of the final state of the system minus the enthalpy of the initial state of the system. Thus, change in enthalpy is also the enthalpy of the substances produced minus the enthalpy of the substances consumed. Now, it is impossible to know absolute enthalpy. We can only measure changes which occur in the enthalpy. Often, internal energy and enthalpy will be identical or nearly identical. This only really breaks down in cases where there is a large number of gas molecules or gas moles changing in the reaction. If I have a large production of gas or a large consumption of gas, which causes a large change in volume, I will see a difference between internal energy and enthalpy, since enthalpy concerns only with heat, while internal energy is concerned with both heat and work. And the relationship between enthalpy and internal energy is expressed as enthalpy equals internal energy plus P delta V. P delta V can also be expressed in terms of gases such that enthalpy change is equal to internal energy change plus the change in the number of moles of gas times RT. As an example of this difference between internal energy and enthalpy, if I have a combustion of ethanol, which is exothermic by negative 1367 kilojoules per mole as its enthalpy change, the work component of this would be negative delta N RT. So the number of difference moles of gas in this, as we start with 3 moles of gas, we end with 2 moles of gas. So the change in number of moles is 2 final minus 3 initial, or negative 1. Plugging this into the work equation, negative 1 times 8.314 joules per mole Kelvin times 298 Kelvin gives us 2.48 times 10 to the third joules, or 2.48 kilojoules of energy as our work component. If the work component is 2.48 kilojoules, then the positive delta N RT, or negative work, is negative 2.48 kilojoules. We can rearrange our enthalpy equation to solve for internal energy such that internal energy is equal to enthalpy minus delta N RT. If I plug in delta N RT, which is negative 2.48 kilojoules, then we have negative 1367 minus negative 2.48, which is the same thing as negative 1367 plus 2.48. If I'm adding to the negative, I'm making it smaller, which makes it go down by approximately 1365 kilojoules per mole reaction. So there's a slight difference in overall energy between the internal energy and the enthalpy, in this case where we see a little bit of a change in the number of moles of gas. Thermochemical equations are balanced chemical equations which express the enthalpy change that is associated with the process. For example, with our ethanol combustion, we have 1367 kilojoules in this process, and it's expressed here on the right-hand side of the equation. In mole terms, a thermochemical equation that is balanced is called a mole of reaction because it is the energy associated with a single mole process, or the smallest ratio of moles in a reaction process. This is abbreviated MOL-RXN, or mole reaction. We can separate out the energy component in a thermochemical equation in this format. So if I take the thermochemical equation, express the actual chemical equation on one side, I'll express the change in enthalpy, or the change in enthalpy of reaction here, being equal to negative 1367 kilojoules. Now in this case, it is important to look at the sign of the enthalpy of reaction. If it's exothermic, like it is in the equation here, it will be negative. If it is endothermic, it will be positive. If I reverse the reaction, I'll reverse the sign. Because a thermochemical equation is always expressed in mole terms, never in molecule terms, we can actually have fractional coefficients involved in a thermochemical equation. For instance, a half of a mole of oxygen. If the number of mole reactions changes, then the change in enthalpy changes by the same factor. If I double the number of mole reaction, I have or have the number of mole reaction, I will double or have the enthalpy. I must always include the state of matter, and usually change in temperature has little. As an example of a thermochemical equation, for the following reaction, how much heat is released by the oxidation of 24.2 grams of aluminum at 25 degrees Celsius and 1 atmosphere pressure? If we have an equation such that 4 moles of aluminum as a solid are reacted with 3 moles of oxygen as a gas and producing 2 moles of aluminum oxide as a solid, with an enthalpy change of negative 3352 kilojoules per mole reaction, I can calculate the number of mole reaction that I have involved here. 24.2 grams of aluminum can be converted to moles by the molar mass, such that I wind up with 0.8962 moles of aluminum. Now, if we look at the equation, the stoichiometric coefficient for aluminum is 4. So in 1 mole reaction of this process, there are 4 moles of aluminum involved. I can convert from moles of aluminum to mole reaction by multiplying by 1 mole reaction per 4 mole of aluminum, which gives me a total of 0.2241 mole reaction. 0.2241 mole reaction times the enthalpy change of negative 3352 kilojoules per mole reaction gives me a total change in enthalpy of negative 751 kilojoules for this particular amount of aluminum. Enthalpy change for a reaction process is referred to as a heat of reaction. If we're dealing with a mole reaction in the process, it's called a molar heat of reaction, or delta H RXN. Oftentimes, measuring heats of reaction uses a coffee cup calorimeter. This literally consists of an insulated coffee cup, and that contains a known volume of pure water. The reaction is run in the calorimeter, and the associated change in temperature relates to the enthalpy change of the molar heat of reaction. In this process, if, say, I have an exothermic reaction, the calorimeter will absorb some of the heat, and the water will absorb some of the heat. If it was an endothermic, it will release corresponding the same way. So the change in heat of the reaction will be equal to the heat that the calorimeter absorbs plus the heat that the water absorbs. So if I'm releasing heat, then it'll be the opposite sign from what the calorimeter is doing. Just like a bomb calorimeter, this process relies on a calorimeter constant, or CCal. Thus, the change in heat of the reaction will be equal to the calorimeter constant times the change in temperature plus the mass of the water times the specific heat of water times the change in temperature. In this process, the reaction is the system and the calorimeter is the surroundings. The enthalpy of a reaction process like this, the molar heat of reaction, will be the heat of the reaction divided by the number of moles involved. As an example of heat of reaction, if I have a 50 milliliter sample of a 0.4 molar solution of copper sulfate at 23.35 degrees Celsius being mixed with 50 milliliters of a 0.6 molar solution of sodium hydroxide at 23.35 degrees Celsius and a calorimeter with a calorimeter constant of 24 joules per degree Celsius, and I have a final temperature of 25.23 degrees Celsius with a density of the final solution of 1.02 grams per milliliter, what heat is released if the specific heat can be assumed to be that of water. The copper sulfate reaction is as given here. If I have a mass of the system will be equal to the number of milliliters, which combined between the two volumes is 100 milliliters, times 1.02 grams per milliliter density, giving me 102 grams of solution. The change in temperature is the difference between 25.23 and 23.35, or 1.88 degrees Celsius. The change in heat of the calorimeter will be then equal to the calorimeter constant times the change in temperature, or 45.12 joules. The change in heat of the water will be equal to the mass of the water, 102 grams, times 4.184 joules per gram degree Celsius, times the change in temperature of 1.88 degrees Celsius, or 802.3 joules. Thus, the overall heat of the reaction is negative 802.3 joules plus 45.12 joules, or negative 847.4 joules, which rounds to negative 847 joules. In this process, sodium hydroxide is a limiting reactant because if I multiply out the volume times the molarity, I find that I have 0.03 moles of sodium hydroxide and 0.02 moles of copper sulfate. Because I need 2 moles of sodium hydroxide for every 1 mole of copper sulfate, I would need 0.04 moles of sodium hydroxide where I have only 0.03, so it is a limiting reactant then. I can convert from the number of moles of sodium hydroxide to the mole reaction by dividing by 2 moles per mole reaction, which gives me 0.015 mole reaction. Using this, I can also calculate a molar enthalpy of reaction for this process by taking the heat of reaction at negative 847 joules and dividing it by the number of mole reaction I have, or 0.015 mole reaction, which gives me 56,460 joules, or 56.5 kilojoules per mole reaction. Now, heat of solution and specific heat can also be calculated in a similar principle. If I'm looking for specific heat of a solid, I can introduce a hot solid to a calorimeter and look at the temperature change that is associated with this to calculate the specific heat of the solid. The heat of the solid will be equal, what can be viewed as what we call Q hot, or the hot aspect of this. The Q cold, the part that is absorbing the heat, is going to be equal to the heat absorbed by the calorimeter plus the heat absorbed by the water. The Q hot, then, is the mass of the solid times its specific heat times the temperature change going from its its hot temperature to its cold temperature. The Q cold will be equal to the calorimeter constant times the change in temperature plus the mass of the water times the specific heat of water times the change in temperature of the cold water. The heat released by the hot solution will be equal to the heat absorbed by the cold solution. Thus, if we rearrange for specific heat, the negative of the calorimeter constant times the change in temperature plus the mass of water times specific heat of water times the change in temperature, all divided by the mass of the solid times the change in temperature, will give me the specific heat of the solid. We can also use this kind of process to find what's called a heat of solution, which is the change in energy associated with the dissolution of a solid in a liquid. The heat of solution is abbreviated QSOLN. Heat of solution will be equal to the negative of the calorimeter constant times the change in temperature, and then plus the mass times the specific heat of water times the change in temperature. It's all negative overall. We could also abbreviate this as negative and then have the whole thing in brackets and have a plus between the two as we do up above. If we don't, then we're just distributing the negative out as we do here in this case. This can also be used to find a molar heat of solution, where the molar heat of solution will be equal to the heat of solution divided by the number of mole reaction involved in that particular sample.